Imagine walking into two science classrooms. In both, students are working with tubs of water, food coloring, and a heat source. Groups are focused, materials are organized, and there's a hum of activity in the air. When you ask students what they're up to, in one room, students say, "We're showing how convection works." In the other, students explain, "We're trying to figure out what makes hot air balloons rise." At first glance, it might seem like they're doing the same thing. Same setup, same observable outcome. Both groups may even draw similar arrows and diagrams as they explain what's happening in the water. But are they really doing the same thing? And does this slight difference between saying convection versus hot air balloons really matter? If students are engaged using science terms and getting through the activity, aren't we headed to the same place? Well, it turns out the thinking required can be quite different. In one classroom, students are performing a task, maybe even doing it well, but they're not figuring anything out. Students are learning about convection. They've been told what it is, and now they're demonstrating it. In the second class, students are trying to figure out why a hot air balloon rises, and that distinction matters. Students are not just hearing about science ideas, they're figuring them out. And through that sense-making, they develop deeper understanding. And to fully engage in the science and engineering practices, it's not enough to learn about a science idea out of context, no matter how creative or hands-on the task. To do the practices, students have to frame their work as an exploration. That means the task has to feel like a puzzle, not a performance. So what does all this mean for your day-to-day teaching? This is where framing comes in. Students are always asking, consciously or not, what am I supposed to be doing here? They are trying to figure out how to frame the work they are doing, and they look to us for clues. If we frame the task as showing how convection works, then they frame their job as following directions and confirming a known idea. But if we frame it as figuring out how hot air balloons rise, then they begin to see their job as making sense of something real. That subtle shift changes how they engage and what they learn. That's one of the biggest shifts OpenSciEd helps us make. Lessons aren't structured around concepts to deliver, they're built around phenomena to figure out. And this type of framing isn't just a one-time thing. Throughout the unit, we have lots of new frames to refer to. For example, in the contact forces unit, one day we frame it as trying to figure out why some things break and other things just get damaged. Another day, we're trying to figure out why bridges bend and don't break. And another day, it might be trying to figure out how to reduce concussions in soccer. The curriculum sets up the sequence and keeps the focus on phenomena, but you play a key role in helping students see how each part fits into the bigger picture. During every lesson, you'll be prompted to work with students to reflect on where they've been, what they've figured out, and where they're headed. This is what we call the navigation routine. The navigation routine will help you continually frame the learning, because otherwise it's easy to fall back into thinking, we're doing this because it's the next lesson. So, as you plan your instruction, use that navigation to ask yourself, how am I framing this? Are we completing a task, or are we making progress on a shared puzzle? What am I planning to say to help students frame their activity around explaining a phenomenon? That small shift in framing can change everything, because when students see themselves as sense makers, they don't just remember science, they do science, and that's what we're really after.